all for joining today's session of the 6G Leadership Tech Talk series organized Bharat 6G Alliance. Bharat 6G Alliance is an industry-led research alliance facilitated by the government. In endeavor to bring you yet another insightful discussion as we explore the intersection of AI, 6G, and GPU accelerated computing, a crucial enabler of the next generation intelligent networks. As 6G evolves, the fusion of artificial intelligence, high performance computing, and real time data processing will be key to unlocking new capabilities from intelligent network automation to immersive holographic experience. Even ITR is working on 6G standards which plans to complete by 2030. The 3GPP will start discussion on 6G this year, aiming to finish it by 2028. AI is said to be the main portion in the 6G era, and it is necessary to transition to an AI native network. There are so many people say that AI for network, network for AI, and that's why today we have the perfect expert from NVIDIA, Ms Anupa, and I am sure that she will be taking through us through all these words in her 45 minutes presentation. This with the slides you can see. Can you just change the slide of ma'am? Yeah, so she is a project manager for NVIDIA 5G aerial converged radio access and edge compute platform. She has over 20 years of telecommunications network industry experience in software engineering and product management leadership, spanning wireline, wireless, satellite networks. What is more important that we are looking towards her, that how can she help our startups, academia in this AI, and there are so many avatars one can say, and there are so many competing figures. I got that. What is its relevance for telecommunications, or one can say ICT? So now I'll be just we will be just listening Ms. Anupa for 45 minutes, and then subsequently we will have structured questions, answers. We have received certain question answers which are shared with her, so she will try to cover under the presentation. If not, then after 45 minutes, we will be having a question answer session with her. You can even type your questions in the chat, which will also be covered wherever required. So over to you, Ms. Anupa. You can just start your presentation. Thank you.
Thank you very much for the warm welcome, and I definitely look forward to this discussion. India is a key country that we are looking to significant innovation as we embark on the 6G journey. And definitely academia in terms of IITs, IISCs, and many, many other universities, colleges, the ability for startups as well as industry leaders to develop networks for next generation, and the opportunity via government and other funding will all collectively enable these three segments of users to accelerate the pace of and help shape innovation towards 6G. So in today's session, let me bring up the slide deck. Give me just a minute here. There we go. Hopefully the presentation.
The slides are visible. Yeah, you can go to the title slide as well, because this one is the second one. Yeah.
Perfect. Perfect. Yeah, so today the talk is about powering AI-driven 6G networks. As was rightly pointed out, AI is part of the baseband networks. AI traffic will be what is really Facebook or Instagram type of traffic. Hopefully, a few years from now, we get to a point where network traffic is predominantly AI data traffic as well. So, today's agenda in the 45 minutes that we have will focus on GPU and CUDA accelerated radio access networks. I'll try to summarize and cover from an NVIDIA standpoint what are some of the key technology and building blocks that we think are essential to help accelerate the pace of 6G innovation. We'll cover aerial AI radio frameworks and try to provide an overview of some of the SDKs, the tools, the platform that we are building, as well as try to maybe cover a little bit in depth on AI aspects, AI frameworks, data collection, training, simulation, developing neural networks. How do you take those neural networks and optimize those neural networks for efficiently running on a GPU? So those are some of the topics that I hope to be able to cover today. We have about 45 minutes, and some of these topics, each one of them, you could spend easily a couple hours trying to walk through. So I'll do my best to keep to the 45-minute time. I did look at the questions that were shared with me, and I have tried to incorporate some of those questions, not all. The focus will definitely be on the baseband, on the access network itself. Certainly if there are questions that I'm not able to cover today, I can circle back with this group and provide an email answer. So as we look at 6G, some of the key foundations that are definitely going to be part of 6G is that 6G networks, they will be software defined, virtualized, cloud native, adaptable networks via RIC or other infrastructure along those lines. And with the fact that they're software defined, meaning that maybe there isn't as much of a custom silicon or PL logic, FPGA logic, you have the opportunity with open source, with access to software, to really enable fundamental research grounds up. You have access to the full stack source code. Another is that unlike generations in the past, networks will be disaggregated and open. And if you follow some of what ORAN has also been doing in 5G and 6G, we are starting to see well-defined open networks, interfaces, and various research organizations as well as industry have started adopting these disaggregated and open frameworks. The concept of ORU, ODU, OCU, a RIC, it's starting to definitely percolate in advanced 5G and is here to stay as we look at beyond 5G. Native AI ML is also just as crucial. When you look at all the KPIs that standards bodies are starting to call out for, AI ML will play a key role in helping deliver networks that help really support these 6G KPIs, be it radio technologies in, let's say, waveform learning or spectrum sensing or semantic communications or intelligent communications. Many others like a digital twin can help with network scale prediction, continuous learning, optimization for energy purposes, the ability to deliver synthetic data, which is all crucial to bringing in AI/ML foundations. With the shift or the movement away from custom silicon, accelerated compute, GPU, and its massive parallelization potential with CUDA to help accelerate the physical layer, that's where you have the most complex compute. And I'll talk about that in a few slides. DPU for fast I/O processing. And last but not the least, digital twin for really being able to plan networks at scale accurately. Those are some of the key foundations as you look at 6G. So from a technologies perspective, and this is a build up here, sorry. So some of the words are not showing up on these blocks. I'll send a different version over as well later. But really, terahertz, reconfigurable intelligent surfaces, joint sensing and communications, AI native air interface, semantic communications, cell-free holographic MIMO technologies. Those are the kinds of technologies that are crucial for 6G networks. So as we looked at some of these needs from a research perspective, some of what NVIDIA has been focused on as a platform is to enable a hardware, software, tools, SDKs, and frameworks that enable innovation, which are open, they're software defined, and help developers or startups continue to optimize towards these shifts in paradigm that are required for 6G networks. So what I've done is divided the presentation into 3 subtopics: aerial CUDA accelerated RAN, that's our reference radio access network; AI radio frameworks, so it's a combination of tools, simulation tools, data collection tools, so tools, frameworks that are building blocks towards leveraging AI. And given the time limit here with 45 minutes, I'm going to skip the digital twin topic today. We can certainly come back to it at another time. All right. So here's if we were to combine all of the different tools that NVIDIA has put together, hardware and software, SDKs and tools and frameworks and simulators, one possible workflow that you can see and use could be along these lines. And the rest of the presentation today, I will peel it apart and I'll focus on and talk about each one of these components individually. But at a high level, in order to orchestrate a closed loop AI workflow, you are looking at the ability to initially collect data. Real data sets are important. It's just as important to be able to get some synthetic data sets so you can scale. You need an ability to train these data sets so that you're able to develop and evolve your machine learning algorithms. Then you need to validate and benchmark to see the optimizations and advancements that leveraging machine learning can help you with. You also need simulation to, again, from an accuracy perspective, to be able to scale. And ultimately, if you deploy in a real network testbed, potentially a private network where you have full control end to end, then in real time, you're also able to benchmark the results of your experimentation, and or any particular advanced capability that you are developing and deploying in test beds or in networks. So some of these tools here are described in this workflow. We have a data lake for front hall IQ sample data collection. This front hall IQ samples, they're nothing but floating point numbers. They can be stored in a data lake database. There's APIs to extract this data into meaningful real world data sets, and you can do this using Jupyter notebooks. A tool that our NVIDIA research team has developed called Shiona is able to then provide the simulation environment to train networks. And you have the result would be a trained neural network. Using the NVIDIA deep learning framework or SDK for TensorRT, you could then take that trained neural network and generate efficient and optimized GPU inference software and integrate that back in with the CUDA accelerated RAN or Ariel and test it over the air using Ariel RAN Colab, which is our end-to-end reference private network. And you can bring your own end devices, or depending on your experiment, a programmable CPU hosted UE allows you an opportunity to really look at different waveforms or research and experiment in the 6G radio space. So again, this was at a very high level, and I tried to cover a lot in that last slide. But that's just an example of a potential workflow. What I'm going to do next is break it into a few different sections and focus on one particular aspect at a time. I've done my best to incorporate some of your questions, but not all. So I'll some of the earlier slides as well incorporated a few questions that some of you had. So let's focus on GPU accelerated Ariel SDK for RAN workloads. So here in this particular slide, NVIDIA, as you all probably are aware of, our company color is green. So wherever there is green in any of these slides, there is some NVIDIA footprint and a product or a tool that NVIDIA has developed to help with that stack overview or the block diagram. So in this particular slide, it's a reference for what we have put together with our Ariel SDK. Ariel SDK is a set of libraries and APIs that provide CUDA-based, inline accelerated physical layer functionality in an ORAN 7.2 split configuration. So the hi-fi of a reference 5G stack is completely inline accelerated and hosted on a GPU. That's number one. Algorithms like LDPC, channel estimation, that benefit from GPU high performance compute, parallelization, and that optimally use the GPU instruction set, including floating point 16 instruction for compute heavy algorithms. Essentially, in this diagram or in this view, there are no proprietary FPGAs. There's no ASICs in the mix. All you have is a GPU, a CPU, and a NIC. The NIC is providing not only the front hall connectivity, but it also is helping support the timing requirements with the slave, grandmaster clock, the sync key support that is required in a cellular network. We additionally are also you're using the CPU to host the L2 and above, and depending on the architecture, you can host a complete network with just these three components: a GPU, a NIC, and a CPU. So this is a bit of a double click on the phi, on the physical layer. Again, the physical layer is where it's computationally most intensive. Fourier transforms, matrix multiplication. Those are inherently the benefits that high performance compute offers from a GPU, from our CUDA libraries. And Ariel has been able to take advantage of the CUDA tools and libraries to completely host the physical layer very efficiently, high performance, and a large number of cells for commercial deployments on a Ampere class or a Hopper class GPU. So just to double click on this particular slide, what you see here is if I go from left to right, on the left it's just a block diagram of a network stack, if you will. And it does use some ORAN terminology. So you have an OCU, ODU, and the high phi, the upper phi, as I described earlier, in a 7.2 split, where the low phi is located in a ORU, in a radio unit. You can definitely bring any and all commercial CUEs or iPhones, robots, dongles, and connect them to this network topology. NVIDIA footprint, again, is depicted in green. It's all of the physical layer, channels, signals, and both data and control, and the algorithms that have been developed not only as a reference, but also optimized on the GPU to deliver very high throughput. So really, from a lower phi perspective, very much, I would say, minimal amount of compute is then required in the low phi in this configuration. Now, a key advantage here. Sorry, these slides I'm having a hard time navigating. Okay, there we go. A key advantage of this architecture is because we are leveraging CUDA C, C++, you have the ability to program at the lowest possible levels on a network just using programming languages like C, C++. Otherwise, if you were doing your development in a programmable logic array or FPGA, you would need experts in that area. As we well know, it's difficult to find that kind of expertise these days. Of course, being software defined has many other advantages. You're very quickly able to prototype and compile and see the results of your experiments on either through some simulations or in a end-to-end over-the-air network. So this was the layer 1 that has been developed by NVIDIA. We've integrated this layer 1 with many commercial L2 pluses. We have key NEPs like Fujitsu, who we are working very closely with, and many others that use the NVIDIA layer 1 and have integrated their layer 2 and core networks. The L2 Plus is hosted on a CPU, and it uses the SCF FAPI interface to communicate with the GPU. Some portion of our NVIDIA stack, the layer 1, is hosted on a CPU to be able to synchronize the GPU workload. Next, what I would like to do is try to cover CPU architecture more from a roadmap perspective. GPU architecture, sorry, more from a roadmap perspective, and where we are headed in terms of SoC as far as forward looking, right? Because we are planning to build these platforms towards 6G. So it's important to keep in mind how the GPU architecture is migrating and what is some of the key technology shifts that are happening as far as even use of GPUs is concerned. So a key highlight or a key transition from a GPU architecture and roadmap that has already started is in the last couple of years, we have started seeing SoCs where there is, instead of discrete components, which are still very much available, for example, Ampere class GPUs. Another example is Hopper GPUs. And data centers, CSPs do use these discrete components. And typically, the connectivity between the GPU and the CPU could be over an external PCIe switch in this case. However, that's where there is potential for bottlenecks. The throughput, the I/O throughput, is controlled by the PCIe links, and it may be slower than what is required to efficiently transport the data from a CPU to a GPU. Grace Hopper is an integrated SoC that leverages ARM CPU, ARM Neoverse V2 CPU with 72 cores. And there is a Hopper GPU. A couple of innovation facets in this architecture is the use of NVLinks. It's a proprietary links between a CPU and a GPU to really deliver fast I/O transfer between a CPU and a GPU. Another key advantage of this architecture is the ability to access 600 gigs of the unified fast memory through the NVLink buses. In fact, this is one of the key innovations in this architecture, that the data transfer is not only fast, but there's also energy savings, and it's an efficient way to transfer data as compared to a more traditional system memory or a DDR memory in earlier generations. So the key point that I wanted to make here was this is an architectural shift that will continue to evolve. Hopper is already available in the market. Grace Hopper is already available in the market. And Blackwell is the next generation of compute. As you're looking at beyond 5G networks, you're planning for networks that will be deployed by 2030. These are some of the key things to keep in mind. There is accelerated compute, the data storage, the data movement, the I/O. That there could be some bottlenecks there, and that this is where there is innovation. The same architecture and some of what I just highlighted applies not only to baseband workloads, not only to RAN workloads, but also for AI workloads, which again, data transfer, and the ability to provide data to a GPU and synchronize leveraging a CPU. So the integrated SoC, a few years ago, our CEO Jensen, he had used this phrase, data center on a chip. And I definitely see that transition shape up in the last couple of years, and more so forward looking. So next, what I would like to do is cover some of the radio frameworks, AI radio frameworks that we have developed. GPUs, CUDA as a common OS for the platform, NVIDIA libraries for deep learning, other libraries that are more focused on compute intense algorithms for math, like cuBLAS, cuFFT. These are a set of tools and frameworks that are available not specifically for 6G, but they're available for all and any AI developer. What we have done is, in addition to these sets of libraries, we have built specific.
We have been working on developing our problem.
Thank you. Thank you. Asta, could you please make sure that everybody is muted, please?
Yes.
Thank you. What we have been doing is developing tools and frameworks, aerial tools and frameworks, towards helping developers with 6G networks. And that's the topic that I'd like to cover in more detail. So coming to really AI frameworks, AI tools, what we have done over the course of the last couple of years is built PyAerial. This provides a Pythonic interface to the SDK. And it's very important to have the Pythonic interface. And I'll cover some of the use cases in detail. But as you look at many, many domains that leverage AI tooling, Python has become one of the de facto languages, if you will, for data scientists and AI/ML developers. And it definitely, from an aerial perspective, from developing advanced networks, this is a crucial tool. As I described earlier in that example workflow, we have a data collection platform that extracts over-the-air RF data, raw IQ samples, and collects them in a database. We then have the ability to do some post-processing of that data and generate meaningful and interesting data sets. NVIDIA Research has developed a tool called Shiona for native ML training and simulation. And we have put together a reference end-to-end 5G conformant and compliant over-the-air network with access to source code. And that's the key here is as developers, as researchers, there's complete access to the source code, which enables you to bring your own modifications through some example blueprints that we have. And you could certainly leverage those blueprints, but it's this ability to then bring in your own innovation, your own optimizations, and help take it to the next level in terms of developing advanced capabilities and advanced solutions. So this particular slide focuses on the building blocks for hardware and software for a reference private network that we have put together. Some of the components, the hardware components, are listed on the left of the slide in the end-to-end system. Going from top down, I described the Grace Hopper architecture earlier. It's this integrated SoC with an ARM CPU and a GPU. Supermicro, this again also highlights the COTS and disaggregated off-the-shelf compute that we are leveraging. But we're using just a standard server from Supermicro with Grace Hopper compute, ARM CPU, Hopper GPU, and a DPU, a Bluefield 3 DPU. The Ariel CUDA accelerated RAN is hosted on the GPU. OAI, Open Air Alliance, is again, it's a group that has access to source on an Apache license based out of France. And they have developed the layer 2 and above, as well as a core reference. And we've integrated the layer 1 with this OAI L2 plus with fairly decent KPIs, about a gig or so downlink, which for open source it's great. Of course, now with Ariel, as I mentioned earlier, we've also integrated Ariel with commercial solutions, and those have much better KPIs because a lot of the radio resource management really depends on the layer 2 and above. We've also integrated this G-Node B, if you will, with a few different front haul switches, Fibrolan, Arista, and so on, and a few others. A grandmaster that we are using is from Viavi. OTA, we have integrated, again, it's an ORAN 7.2 split. So definitely you could use other certified and badged ORAN radios. In our case, we've integrated with Foxconn as one of the vendors, and there's a couple of others that we've integrated with as well. Now, as we look at beyond 5G, what I described up until now was still more or less at the baseband layers. It's important to also make sure that the endpoints are also programmable, which is hard, right? I mean, you typically don't see access to an iPhone source code or a Samsung UE source code. So what we did is we've used OAI's soft UE, and for an RF front end, we are using an NI radio And now, as a result of this, you really have end-to-end programmability even at the device, at the end device. So you can change the behavior of a core node, you can change the behavior of a scheduler, you can change the behavior of the physical layer, the layer one, or you can change the behavior of a UE. And I think this is one of the crucial points here is the ability to change behavior is also an opportunity to bring in machine learning where there is an optimization potential. When you have closed loop systems, when you have proprietary libraries, when you do not have access to source code, you cannot not only change behavior, but you are not going to be able to really figure out neural networks or trained algorithms that will bring optimizations into your end to end. I think this slide I'm just going to very quickly walk through. There's clearly lots of tools and frameworks that are necessary for enabling 6G. Even the development of 6G requires simulation tools, requires multimodal data, requires how do you integrate machine learning capabilities? How do you model at scale? How do you plan networks at scale? When you have, from a radio technology perspective, large number of bandwidth, large number of devices, large number of antennas, how do you start developing some of those technologies? So these are just a few key points that we are definitely keeping in mind as we develop tools, frameworks, SDKs for the advanced networks of the future. So the next tool that I want to focus on is Shiona. Shiona is our GPU accelerated framework for fully differentiable link level simulation. What Shiona does is enable developers to very quickly prototype. It has native support for neural networks. It can scale from one GPU to multi GPU setups. And some key advantages of Shiona is it's extremely well documented with example code. And not only do you have example codes, but with the click of a button, you can deploy this code or Jupyter notebooks rather in a Google Colab environment, which means you do not need any accelerated data center or a lab with hardware resources on prem. You can use the Google Colab, which is a data center run by Google for research and for development, and you can just click through these code examples. It also uses an Apache license. It's free and open source. So this particular tool, in my mind, it's one of the easiest ones to start using if you are just onboarding or if you're just starting to use NVIDIA tools and frameworks. As I mentioned earlier, the source code is available on GitHub, lots of tutorials and documentation and white papers. It's released with an Apache 2.0 license. It welcomes contributions from developers. You can certainly fork the Shiona repository. You can write your own code. You can document it. You can submit a pull request. And there is GitHub tooling for new feature requests and so on. Shiona was released earlier as compared to some of our other tools and frameworks. And at this juncture, it is definitely, you're seeing papers and um, prominent researchers highlight some of their findings. So you definitely are going to find Shiona more and more in advanced research towards 6G. And this slide here is just highlighting some of these examples with prominent groups, be it Keysight or Rhodes and Schwartz and MWC as well. There was significant press around Shiona. The next tool that I want to cover is taking us, back to really figuring out how do you collect data so that you have the data sets that are required for machine learning algorithm development in Shiona. So one such workflow is depicted here. These are now real data sets, or the ability to collect real data running on a over-the-air network. And the tool that we've developed, it's called Aerial Data Lake. What it does is it captures over-the-air data in real time on an reference 5G network. It's assuming a 7.2 front-haul split. This data is stored in a ClickHouse database, and we have developed APIs to extract data from these data sets, from this database, to be able to generate useful data sets that can then be used for training purposes in Shiona. The next tool that I would like to be able to cover is PyAerial. I described it earlier as this is a key mechanism that across many domains, not just networks and not just signal processing, but Python has really become a language for data scientists and for machine learning. Similarly, for wireless communications, we've developed PyAerial as an abstraction or as a set of APIs that are really bindings to the CUDA accelerated kernels that have been developed for Aerial. It's relatively lightweight, and it's mainly used to create Python bindings of existing C++ code. So from a user's perspective, from a developer's perspective, you can call CUDA accelerated functions from Python. You can use it as a part of your design workflow, from simulation to taking it to a real operational API, if you will. And it also helps in verification of a TensorRT optimized inference engine. Yeah, these are examples of some of the components. You can see the typical physical layer channels and some estimations, some algorithms here. There are many Jupyter notebooks which are on the developer page that you can also browse through. So key use cases for PyAerial are the following. You can certainly collect data with the data lake, as I pointed out in the earlier slide, and generate training data sets. You can start with a PyAerial model of a particular pipeline, if you will, and you can replace those components in that pipeline with TensorRT, right? So that's your optimized inference software. You can start with PyAerial and model a pipeline. You can simulate by incorporating your own algorithms in Python or another language that has a Python binding. You can do some post processing of the data that was collected, so you can visualize and analyze that data. You can use Python for online training by batching data that was captured in data lake and then translating that data into generating training data sets, and then use the inference engine with these new parameters that you've developed. So here's an example of how you could use PyArial for data visualization. In interest of time, I'm going to, feel free to read through it. I'm going to skip this slide unless there's a particular question that comes up. What I wanted to do is focus on the next slide here, which is highlighting how you can generate real-world training data sets using PyArial. So the training data here is identical to the corresponding node, I guess, in a real-time over-the-air pipeline. It's the same algorithms, same CUDA code that is used for PyArial, as well as the Arial RAN. Now, in this particular view, what you see is, let's just say this is the Phi pipeline where you have the channel estimate, the MMSC, the equalizer, soft demapper, rate matcher, LDPC, and CRC. Let's say this is your pipeline. At any points in between that pipeline, you can collect data. So in this particular example, the Arial data lake is an LLR data lake, if you will, in between the equalizer and the soft demapper. You can use a API and from our examples to extract data from the data lake. And then this particular LLR net, or LLR dataset can be leveraged by Shiona to generate a neural network, to generate an LLR net, if you will. Once you have your trained neural network, you could then potentially, leveraging TensorRT, extract efficient GPU inference software, and then validate and benchmark this in an over-the-air network if that's an experiment or that's where your feature is headed. So here is an example of this particular closed loop view. And a few things to highlight in this slide are, again, TensorRT, it's an NVIDIA SDK for deep learning inference. That's predominantly where TensorRT is used. And it includes deep learning inference optimizer as well as a runtime that delivers very low latency, efficient GPU code for inference applications. And we are leveraging the same in the wireless networks. So let's say you generated your data set, you developed your machine learning algorithm, you trained in Shiona, and you have a trained neural network. Where TensorRT could be useful potentially is to is towards weights and activation calibration by maximizing the throughput um, while preserving the accuracy of your generated neural network. It helps optimize the use of GPU memory by fusing nodes in a kernel. It also helps with kernel auto tuning to select the best data layers and algorithms based on a target GPU platform. It is able to minimize memory footprint, and it is able to reuse the memory for tensors efficiently. It's scalable to process multiple input streams in parallel. And it is also able to optimize recurrent neural networks over time steps with dynamically generated kernels. So TensorRT, again, it's a standard NVIDIA SDK for AI workloads, for deep learning inference workloads. And we've been able to leverage TensorRT here in advanced cellular networks to really help transition from once you have a trained neural network, leveraging TensorRT, you can generate GPU optimized inference APIs, inference software that you could then, using C++, validate in a real network, or using the Pythonic bindings, convert it into GPU efficient software. How are we doing for time, Asta?
You can.
You can, like 5 minutes more, you can go and then we can have question and answer.
Perfect. Yeah. So I'm pretty much on the last slide here. With really now, the what we covered, and just to kind of summarize what we covered so far, through this example workflow again, it's the following. For just like in all domains, all AI domains, be it healthcare, be it robotics, data is crucial. The ability to generate data, data sets, it's important for training or developing of machine learning algorithms. So what we've done is created a tool, data lake, that can help collect data. And then, we have APIs, Jupyter notebooks that can help do post-processing of that data to generate interesting data sets. Once you have data sets, now data, again, these data sets can be real data sets, or you could generate synthetic data. And I went through one slide with a particular example of how you can generate a synthetic data set. Once you have a data set, then training is the vehicle by which you will develop your machine learning algorithms. At NVIDIA, the tool that we've put together for wireless networks is Shiona, for link level simulation, for training, for link level training. We walked through and covered, once you have a trained neural network, how you can make use of TensorRT, which is a deep learning inference library from NVIDIA, to develop efficient inference APIs or efficient GPU optimized software. And then, a few things that ultimately you may choose to do is deploy these or integrate them using C++ in an API, or use Pythonic bindings to convert them into GPU efficient code. And the key is the ability to then validate and benchmark in a reference network, I'll again touch on some of the key enablers for this technology and a technology shift that is occurring at the moment. And those key enablers here are being software defined. So everything that we looked at today, it's virtualized, Docker containerized, there's just software, there's no other proprietary or any ASIC or hardware required. It's just a combination of CPU, GPU, and a NIC, and virtualized software. Another key foundation is ability to have complete access to source code, and that's where as a developer,
I think you can see. Can you see the public chat?
Yes, I can see the public chat.
Yeah, so I think Dr. Rizwan, I think earlier he raised the hand very beginning. So Dr. Rizwan, do you have anything to ask? These were the various respondents. They just wanted to ask certain questions which were shared with you.
Yes.
And I'm sure that you might have covered.
I tried to cover some of them, not all, and I'm also looking at the chat window now.
One question I have, whether whatever you have shared is your NVIDIA confidential, or can it be shared with the today's participants?
We have shared some of this material in other forums as well, so please feel free to share with the participants.
Thank you. So I think all the participants who are here will be just sharing on the email the presentation done by you. And the next is, I think you can see the Mr. Jatin Grover. I think these are the questions. I think these are the questions.
So I take some of the questions back and forth from the. I have these questions. They were shared earlier, so I'm going to go back and forth maybe with the questions from the chat window and some of the questions here. So there's one question on the chat window, and I'll read it out loud. LDPC channel estimation equalization, are they implemented using AI methods? So the answer is no, they are not implemented using AI methods. They are implemented using CUDA CC++. These are all algorithms that the standard 5G reference stack uses and leverages. This is where research is, it's ongoing. And this is also potentially an opportunity for where key NEPs may want to differentiate themselves. Even in past generations, the tier ones, Nokia, Samsung, Ericsson, they've all had some secret sauce, if you will, that led to performance difference amongst themselves. So I expect key areas of research and innovation for sure. And I expect that novel techniques and AI methods will be used in beyond 5G networks. Yeah, I don't know, will the video recording be available to everybody?
Yes, it will be actually it is live on YouTube, so they have the access of it all. Yeah.
Perfect. So there was a question on the compute power. So 6G standards are really calling out for energy efficient compute. So, that's certainly some of the goals from a standards perspective is to conserve energy. Will they require high compute power in the devices. So the end devices are also transitioning and shifting even as we speak. Your end devices are devices like robots, fairly compute intensive, that might require high power, or the end devices are thin devices, which means they have very limited compute. Um, for example, headsets, the Meta AR Ray-Ban glasses is a good example of that. If you look at the form factor, they just look like glasses, but there's definitely some compute in there. You're able to speak to. There's a conversational AI there. So more and more, it's a difficult question to answer whether the compute power in mobile devices will remain unchanged. I do expect devices will be developed at these spectrums, right? There would be devices that are very thin client kinds of devices that are serving a single purpose. And then there may be robots that are robo taxis that are really complete data centers in themselves, if you will. So there was another question on KPIs. So before I take the KPI question, somebody has their hand raised. So please, if you want to ask your question.
Yeah, Mr. Bahubali.
Yeah. So thank you for wonderful session uh, from your side, Anupa. Like I wanted to know, I'm more curious about since it is an RF, always environment will keep on changes. There will be effect on the transmission and also at the reception side. So, wanted to know, will that today's 6G networks has an use of agentic AI kind of a thing, where it dynamically changes as per the channel condition. Your inputs on it.
Yeah. So definitely, I think that networks in the future, adaptive networks, you're absolutely right. RF conditions keep changing, and the ability to optimize a network in real time for these changing radio conditions is crucial. Machine learning and AI is just yet one more tool, if you will, that operators can leverage towards developing these techniques so that networks can be optimized for the changing radio conditions. Absolutely. And they can self-optimize and self-learn as well, because if you develop that closed loop, you're able to develop intelligence.
Right. In top of it, you would like to, as in as in technical side, it should be at the local side, or it should be at the base station side. Your comments on it.
So, just like I answered the previous question, there is many kinds of end devices.
Right.
Right. Some are. So my thought is it will depend on the device. In some cases, you have devices communicating with each other. The topology of the network, there is also research going on as far as whether they will stick to the traditional cell sector definition, or there may be cell-free topologies with maybe a central scheduler of sorts, if you will. So these are all good questions, and it's definitely advancement possible in these areas.
Yeah. Thank you. Like being an startup, if I am thinking like as a startup. So can I think like agentic AI is another avenue wherein people can explore it.
Yes, absolutely right. I mean, one of the key things that so we are already now in this shift where there are these large language models
Right.
and blueprints for being able to use these large language models.
Right.
However, agentic AI is definitely an area that is bubbling to the surface as well. It's an opportunity to focus on these AI agents, if you will, to being able to provide a more holistic solution down the road, depending on the domain, depending on the knowledge of the some proprietary conditions, be it in an enterprise or be it in a radio environment.
Yeah. Thank you, Anupa.
Can you take some more questions from the chat and then we can.
Yeah, happy to do that. So, how can startups utilize? So I'm going to from an NVIDIA perspective, I think I'm going to try and summarize that. We are a platform company, and it's a given at this juncture that GPUs and high performance compute have a role to play as you look at advanced networks. One of the key ways that we try to enable developers and enable the ecosystem is by providing access to source code, access to SDKs, through a very straightforward early user license agreement. And as long as it's for your initial development purposes, for your research purposes, you have access to the source code. When it gets into commercial networks, that's when there is a long-term license and support kinds of licensing. So that's one of the key ways that I feel startups can really start taking advantage of all these tools that we've developed. Apache licenses and so on. It just hopefully encourages academia, startups to use these tools, SDKs, APIs. Also, through your contributions, I think it helps accelerate the developer ecosystem as well. So with some of the reference toolings, frameworks, it's an opportunity to just quickly focus on the innovation instead of the building blocks. So that's what I'd like to say here. And I don't know if we're almost out of time now. So
Yeah, so I think Neelam's she has asked certain questions. If you see,
is it still calling this a reference, or is it now that it is commercial? Is it far? Yeah. So the reason to so I'll answer it in two ways. As we look at beyond 5G, some of these tools, frameworks, we are still developing them. Therefore, it's a reference. As we look at a particular deployment scenario with a particular configuration that's hardened and mature, that's not a reference anymore, right? It has commercial grade KPIs. So I hope that I make that distinction clear. We're definitely targeting commercial deployments for advanced 5G with hardened KPIs and so on. But as you look at 6G and the advances and the tooling and the frameworks, the data collection, we might consider optimizing some facets of particular libraries. It's still a reference. So that's the way I like to think about it, as a commercial hardened deployment for a particular scenario, be it massive MIMO or be it a particular configuration, with one hardened scheduler and in a kind of a network scenario versus being a reference for generic use. Is OAI code available in GitHub? Yes, it is. And it is integrated with Ariel, not the SDK, but Arc OTA. In one of the slides, I had references to Ariel RAN Collab, the end-to-end reference network that we have put together. That has gone through our own test and qualification with our QA team. So it is integrated. It is another question was on a 7.2 split and its suitability for 64T 64R. The answer is yes, it is. It is. The software is totally suitable and capable of 64T 64R configurations.
So I think with this, let us. It's time to thank you and my entire team with Dr. Astha, Mr. Gyanendra, Swapnil, and Faisal have worked. Now I request Dr. Astha Sharma to give the vote of thanks to you. And really great. I'm thankful to all the participants. We'll be sharing the PPT. This is available on YouTube. So over to Dr. Astha Sharma.
Thank you so much, sir, and thank you, Anupa. So, as we conclude this insightful session, it is my privilege to deliver the vote of thanks on behalf of Bharat 6G Alliance. And definitely a very heartfelt thanks to Anupa Kelkar, our esteemed speaker, for sharing her deep insights into the transformative role of GPU accelerated computing in AI driven 6G networks. It was really very fantastic talk, and we got a very good response from the participants who are eager to work and explore this new realm of AI and the role of GPU. And I hope that our India as a country also leverages the technology and go ahead. So, and definitely it's very fun to listen to you, Anupa. You're a very good orator. And if a teacher is good, then definitely students, they just don't learn, they become eager to learn and innovate. So thank you for that. And thank you for your precious time as well.
Very much for inviting me. Again, as I highlighted earlier, networks of the future, I mean, there's no doubt they'll be AI driven, AI powered, AI infused, and the kind of traffic that these networks will transport is also going to be AI traffic. So we are in a very, it's a cusp of a technology transformation. For those of us that have been in this industry for a while now, I think this is one of the best times to be in this space. I truly believe that. And thank you for inviting me for this presentation. It would be great if I have a sense of who the participants were. So maybe if I can please ask you, Asta, to share that with me.
Definitely. We will
Thank you.
share
Namaste. Namaste from India.
Thank you very much.
And I
Thank
will
you.
also thank all the participants as well for actively engaging with their thought-provoking questions as well, because the audience is also very good. We received a good response.
And please share PPT. I think just.
Yes, we will be definitely sharing the PPT.
Thanks, Anupa. Rajesh sir, wonderful. So thanks, Anupa. This is Mangal, and good connect back to you. It's really wonderful to see. And I hope now we can work very closely, India, this WISE group, and our Bharat 6G Alliance. Okay?
Yeah, sounds good. Thank you very much. Bye now. Good night.
Okay, good night.
It's good day for us.
Yeah.
Started good night to you. Yeah, definitely. Thank you.
Thank you.